Let's take a look at a few applications of quadratic equations, some word problems where we can use what we know about quadratic equations to solve them. We can use quadratic equations to solve geometric problems like we did with linear ones. And in fact, having a knowledge of quadratic equations allows us to solve problems involving area, which linear equations usually aren't up to. So for instance, we could look at the following. A rectangular garden has a total area of 36 square meters, and its length is 5 meters longer than its width. What are its dimensions? Now, the strategy that we're going to use here is the same as the strategy that we used when we were doing problems with linear equations, and that we're going to use for all of the problems that we look at. We're going to need to start by identifying what the unknown quantity is, or one of the unknown quantities, give that quantity a variable name, express the other quantities in the problem in terms of that variable, and then find some sort of equation that either relates the variable expressions to something that we know, so relates the things that we don't know to something that we do, or we have to find a way of expressing the same quantity in two different ways so that we can set those two expressions equal to each other. So in this case, the problem is asking for the dimensions of the garden. And we can sketch out the garden, as is usually a good idea with geometric problems. Sketching out the situation to keep track of things is usually a good idea. And so we are asked to find the dimensions of this garden. And so using one of the dimensions as the variable is usually a good idea. As I mentioned before, typically it's easier to use the smaller values as your variables when you have a choice. So in this case, we'll go ahead and we'll let W be the width of the garden. So that's a W right here. And we need to specify that this is being measured in meters. All right, we are also told that the length of the garden is 5 meters more than the width. This means that to express the length, we don't need to introduce a new variable because we know how it relates to the original one. So we know that if the width is written as W, then the length can be written as W plus 5. So the length is W plus 5 because we're told in the problem that the length is 5 meters longer than the width. We're also told that the area of the garden is 36 square meters. But we also have another way of getting at the area of the garden because we're told that the garden is a rectangle, and we know from geometry that the area of a rectangle can be calculated by multiplying the length and the width together. So the area of the garden is the length of the garden times the width of the garden, and we have expressions for both of those. The length of the garden is W plus 5, and the width of the garden is W. So we have two different expressions for the same quantity. On the one hand, we know that the area of the garden is 36 square meters, and we also know that the area of the garden is W plus 5 times W square meters. Well, since they're measuring the same thing, they have to be equal. So therefore, 36 must equal W plus 5 times W. And now we can treat this as just an equation sitting by itself and solve it just using our normal algebra techniques. So we can expand the right-hand side, get this as 36 equals w squared plus 5w. We can subtract 36 from both sides and be left with 0 equals w squared plus 5w minus 36. And now we have the quadratic equation in standard form, which is usually what we want to do first. So now we need to go and solve this. Now typically it's faster to try to solve an equation by factoring. We usually want to try that first rather than jumping immediately to the quadratic formula. Because even though the quadratic formula always applies and can always give us an answer, it's slow. Applying the formula, making sure that you've got it all correct, and simplifying it all down, it takes some time and has a lot of steps to it, a lot of opportunities for error. Factoring, when it works, is much faster. So that's what we're going to look at here. We want to say, is there a way to factor this polynomial? And so in this case, because the coefficient of w is 1, we're looking for two numbers that multiply to equal negative 36 and add to equal 5. If you think about that for a while, you'll wind up with the numbers 9 and negative 4. They have a product of negative 36, and they have a sum of 5. And therefore, this polynomial factors as w plus 9 times w minus 4. From here, we can use our zero factor theorem to say that, well, this means that either w plus 9 has to equal 0, or w minus 4 has to equal 0. Which means that either w equals negative 9, or w equals 4. Now, if this problem were just an abstract math problem that said solve the following quadratic equation, then we would stop here and we'd be done. We'd have two solutions. But this isn't. This is a word problem, and so the solving of the quadratic equation is only part of the whole process. We need to go back and interpret our answer in terms of the original problem. And in particular, when we're dealing with problems involving quadratic equations or more complicated equations, we will often have multiple answers. And so we have to see whether all of the answers that we have make sense or not. Very often it'll be the case that some of the answers that come out of the pure math don't make sense in the context of the problem at hand. In particular, let's consider the solution w equals negative 9. Well, w was supposed to be the width of the garden measured in meters. And a width of negative 9 doesn't make sense. We don't consider negative distances in geometry. We don't consider negative lengths or widths or anything like this. And so we're going to eliminate this answer. This answer of negative 9 doesn't make sense for this problem. We'd also eliminate something that had w equals 0, for instance, because a 0 width also doesn't make sense in the context of the problem. On the other hand, the solution w equals 4 does make sense. A width of 4 meters has a meaning that we can talk about. So this shows us that the math gives us two possible answers, but only one of them makes sense in the context of the problem. And so that's the one that we're going to respond with. Now, of course, the problem asked what the dimensions were. So we're not going to answer w equals 4. That doesn't make any sense in the context of the problem. But we can answer that the garden has a width of 4 meters and a length of 9 meters. And that's because we know that the length of the garden is 5 meters more than its width. So the answer to the problem is that the dimensions of the garden are 4 meters by 9 meters. Now, in this case, it's easy to go back and check to make sure that the answer that we've got is a solution to the original problem. We want to make sure that a garden with a dimension of 4 meters by 9 meters has a total area of 36 square meters, and it does, because 4 times 9 is 36. And we want to make sure that the length is 5 meters longer than its width. And it is, because 9 meters is 5 meters more than 4 meters. So, we have our answer, but notice that we had to throw out one of the numbers that we got. This is a very common thing that we run into when doing applications of quadratic equations. Let's see another one. A boat has a speed of 10 miles per hour in still water. A camper takes the boat 4 miles downstream, that is with the flow of the river, then 4 miles back. Upstream. The return trip took 10 minutes longer than the outgoing trip. What is the speed of the river? That is, how fast is the river flowing? So let's make sure that we understand what's going on here. We've got someone who is camping, so they've got a campsite over here, and they're taking their boat 4 miles downriver, and this is the direction that the river is flowing. And so the speed of the boat is going to be faster than it would normally. The boat normally has a speed of 10 miles per hour, but when it's going downstream, it's going to have a speed that's higher than that because it's being carried along by the river. But then on the way back, it's fighting against the current. And so the speed of the boat is going to be less than 10 miles per hour. So let's see if we can write down some of the unknown quantities involved and see if we can come up with some sort of relationship here. So first of all, our unknown quantity is the speed of the river, is how fast the river is flowing. So let's let R be the rate at which the river flows. Now, the problem didn't ask us for any particular units here, but the problem gave us speed units in the problem of miles per hour, so that's how we should answer. We should always answer a problem using the same kinds of units as the problem originally asked them. In the previous problem, we were given metric units. We were given meters in the problem, and so our answer was in terms of meters. In this problem, we're given information in terms of miles per hour using imperial units. We should then give our answer in terms of miles per hour and imperial units. So we have that R is the rate at which the river flows in miles per hour. Now, for each one of these trips, downstream and upstream, we can look at the distance, the rate, and the time. And we can recall that the distance traveled is equal to the rate at which the object traveled times the time that it took. Now, we know the total distance traveled on both trips. The boat traveled 4 miles, both downstream and upstream. Now, the rate at which the boat traveled was different in each case. Now, going downstream, the rate of the boat was the normal 10 mile per hour speed at which the boat went, plus the speed of the river, because it's being carried along by the river. And going back upstream, the rate of the boat, the speed of the boat, was 10 miles per hour minus the speed of the river, because it's fighting against it. And we don't know how much time was being taken going downstream or going upstream. So this time we'll go ahead and introduce a couple more symbols here, but they're going to be just, we're just going to use them for a second until we can actually work out the problem. So we'll go ahead and let T down stand for the time that the boat spent going downstream, and T up for the time that the boat spent going upstream. Now we are introducing new symbols here, so we should be precise about this. So T down is the time spent going downstream in hours. Now this is very important. When you look at the distance equals rate times time formula, everything absolutely needs to be consistent. This rate that we're working with here, the 10 plus r, this is being measured in miles per hour. That is miles per hour. And therefore this t must be measured in terms of hours in order to be consistent. And similarly for the upstream. So T up is the time spent going upstream in hours. Now, let's look back at the problem and see what else we're told. What piece of information haven't we used yet? We haven't used the fact that the return trip took 10 minutes longer than the trip down. So we're also told something about the difference between these two times. We're told that the time spent going upstream was larger than the time spent going downstream. Well, we could have figured that out already because the boat's moving faster going downstream, but we're told specifically what the difference is. Now, notice that the problem tells us that the difference between the two times was 10 minutes, but we need to express things in terms of hours. So we need to convert this 10 minutes into hours. And so 10 minutes is 1/6 of 1 hour. Now we could figure this out in the following way, if we didn't see it immediately. We could say 10 minutes this is what we're starting with, and we're going to multiply this by a conversion factor. And the conversion factor is going to be something that tells us how we change from a number of minutes into a number of hours. And what we're going to do is we're going to multiply by, well, basically 1. We're going to put the same amount of time on the top and bottom of this new fraction we're multiplying, but we're going to measure it in 2 different ways. We're going to put 60 minutes on the bottom and 1 hour on the top. Now, this works because units can actually cancel like variables do, like numbers do, like expressions do. And so if I have 10 minutes times 1 hour over 60 minutes, I can cancel the minutes. And so I'm left with 10 over 60, and that's in terms of hours, or 1/6 after I reduce. And the whole point of the conversion factor is that 1 hour equals 60 minutes. And so multiplying by 1 hour divided by 60 minutes is basically just multiplying by 1. So the whole point of this is that we're told that the return trip took 10 minutes longer, or in other words, it took 1/6 of an hour longer. So the difference between the time spent going upstream and the time spent going downstream is 1/6 of an hour. Now, to actually get this to a place where we can use it, we're going to solve each of the distance equals rate times time equations for the various times. Now, if I take this downstream equation right here and I solve for t down, I would divide both sides by 10 plus r. And so the time spent going downriver is 4 divided by 10 plus r. And I got that just by solving that equation for t down. And similarly, if I solve for t up in this upstream equation, I get that t up is equal to 4 divided by 10 minus r. So the time spent going upstream is 4 divided by 10 minus r. Time spent going downstream is 4 divided by 10 plus r. And we're told that the difference between those two times is 1/6. All right, that was a lot of setup, but now we actually have an equation that we can work with. So let's go to another page to finish this problem. So our equation from the previous page said that 4 over 10 minus r minus 4 over 10 plus r is equal to 1/6. And this is what we want to solve for r. As we've done a few times, we want to multiply both sides by the least common denominator of all the fractions involved. So in this case, the least common denominator is going to involve a 6, because you've got that 6 in the fraction on the right, and it's going to involve a 10 minus r and a 10 plus r, because those are the two factors that appear in the other two fractions. So we're going to multiply both sides by this least common denominator, and I'm going to go ahead and distribute that through on the left already and write it as 6 times 10 minus r times 10 plus r times 4 over 10 minus r minus 6 times 10 minus r times 10 plus r times 4 over 10 plus r equals 1 over 6 times 6 times 10 minus r times 10 plus r. We get cancellation, as we've seen a few times so far. Cancellation of a bunch of denominators. And so then let's see what we get. This first term will become, we've got a 6 and a 4 being multiplied, so that's a 24 times 10 plus r, minus, again, a 6 times 4 is 24 times 10 minus r. This equals 10 minus r times 10 plus r. Expanding all this out, we get 240 plus 24r minus 240 plus 24r when we distribute everything through on the left. And on the right, we get 100 plus 10r minus 10r minus r squared. So we have lots of cancellation going on. When we simplify the left-hand side entirely, we get 48r. And when we simplify the right-hand side, we get 100 minus r squared. So we've simplified everything down to just a quadratic equation. Now we want to get it into standard form. So we want to get the r squared and the 100 and the 48r all on one side of the equation. In order to make the coefficient of r squared positive, I'm going to go ahead and add r squared to both sides and subtract 100 from both sides. In order to get r squared plus 48r minus 100 equals 0 as the equation I'm looking at. So we have r squared plus 48r minus 100 equals 0. We want to solve this quadratic equation. We always want to start by seeing if we can factor. We would be able to factor this if we can find two numbers that multiply to equal negative 100 and add to equal 48. Well, once again, that's something that we can do. And we can get r plus 50 and r minus 2. And those two numbers add up to 48 and multiply to negative 100. And so there's our factorization. So when we simplify our equation, get everything into our standard form and factor, we wind up with r times 50 times r minus 2 equals 0. We can now use the zero factor theorem to say that therefore r plus 50 equals 0 or r minus 2 equals 0. So we get r is equal to negative 50 or r is equal to 2. Now we want to check and see, well, which of these makes sense. We can go back and double check what r was. R was the rate of the river. It was the speed at which the river was flowing. And the river was, of course, flowing downstream. And so a negative value for r doesn't make sense here. Negative speeds don't make sense in this context. And so, again, we're going to throw out one of our equations. Very often, it's the negative solution, when we have a positive and negative solution, that we wind up throwing out. Now, not always. There are some cases where negative values do make sense. If we're talking about temperatures or bank balances or any one of a number of things, negative numbers can make sense, but it's often the case that they don't. So in this case, r equals 2 is going to be the solution that we work with. Now, again, going back to the original statement of the problem and our original working of it, we see that the question asked, how fast is the river flowing? And r is the rate of the river's flow. That's the way we set it up. So our answer can now be the river is flowing at 2 miles per hour. And there is our answer. We had to work a bit at it. We had to set up an equation, which wound up being a rational equation. We had to cancel out all those denominators before we even got it to a quadratic, and then we had to factor it and work it out, but we got there. Now, if either of the quadratic equations we ran into in these two problems hadn't been factorable, we would have gone straight to the quadratic formula and just used that. But we didn't need to in these cases. All right, let's do one last example, and I promise it'll be quicker than the previous one. A ball is launched from ground level with an initial upwards speed of 32 feet per second. Its height after t seconds in feet is given by h equals 32t minus 16t squared. When does the ball hit the ground? So this problem is a little bit unusual in that it gives us a lot of stuff already that we usually have to work out on our own. For instance, it has defined the variable t and the variable h, and it's even given us an equation to work with. We only have to do a little bit of work to get this into an equation that we can solve. Now, we could actually derive this assuming we had a sufficient knowledge of physics. Turns out that this equation in this problem is not from nowhere. It's not just made up. This is, in fact, what the height of the object would be, assuming it was launched upwards with a speed of exactly 32 feet per second, and assuming we ignore air resistance. But this formula is not just made up. There's a real good meaning to it, and so this isn't just an exercise here. There's something real to it. So we know that the relationship between the height of the ball and time is given by this equation, h equals 32t minus 16t squared. We want to know when the ball hits the ground. That is, we want to know some value of t. What we need to do is we need to translate what the ball hitting the ground means in terms of h, the other variable. So what does this mean in terms of h? Well, for this, we want to, of course, remember what h means. The problem says that h is the height of the ball in feet. Now, when the ball hits the ground, its height is going to be 0. If its height is positive, it's above the ground. If its height is 0, it's on the ground. So our answer to this question, to the question in red, is that this means h equals 0, i.e., we want to find the t that makes h equals 0. So that means that we can plug 0 in for h in the given equation, which will give us 0 equals 32t minus 16t squared. So this will tell us when the ball has a height of 0, i.e. when the ball actually reaches the ground again. So we want to solve this equation. Because we've got different powers of t, we can't directly solve for t. We're going to have to use the zero factor theorem somehow. But we can factor the right-hand side by factoring out common factors. So we ask what factors are in common between the two terms here, the 32t and the negative 16t squared. Well, we can certainly factor out a 16, and we can certainly factor out a t. And if we do that, we leave a 2 minus t behind. So now we have an equation that says that 0 is equal to the product of 16t and 2 minus t. And so that means that 0 equals 16t, or 0 equals 2 minus t. And we can solve each one of these individually. We can divide by 16 to get 0 equals t on the one hand, or we can add t to both sides on this equation to get t equals 2. So then, again, we want to see which of these values make sense. Now, only one of these values is going to be an answer exactly to the question that the problem asked, but we've got a little bit of a different situation here than we did in the previous ones, because both of these values of t correspond to something that's actually happening in the problem. So the t equals 2 answer, this is going to give us the full answer to our problem. This tells us that when t is 2, that is 2 seconds after the ball is launched, the ball's height is going to be 0 again, because that's going to be a solution to the equation that we worked with. So it's going to take the ball 2 seconds to go up into the air and to come back down to have a height of 0. But it's also accurate to say that when t equals 0, the ball has a height of 0. Because the ball started from ground level. The ball started with a height of 0 right at the beginning of the experiment, when t is 0, at the beginning of time as far as this experiment is concerned. So the t equals 0 solution here has meaning. It's just not an answer to the specific question that's being asked in this problem. So you'll see this sometimes. You'll be working a problem and you'll find that the math tells you things. In this case, the math is telling us both that the ball hits the ground after 2 seconds, but also that the ball was at ground level at the beginning of the experiment, which is something we already knew, but it's a confirmation of that, and sometimes you can get more things out of the math that you didn't expect or didn't know ahead of time. However, in this case, t equals 2 is the answer that we care about for this problem, and so the answer to the question is the ball hits the ground after 2 seconds. And those are a few examples of how we can use quadratic equations to solve word problems, application problems.